Relations. I'm happy to be back to Fukuoka after, say, more than 4 years. So today I'm talking about cryptography from group actions. It's just a little bit about myself. So I finished my PhD in math in Leiden University many years ago, so 9 years ago. And then I do 2-year postdoc at Bielefeld University in the Faculty of Mathematics for 2 years. Then I moved to IMI Kyushu University on October 2015 until June 2018 as assistant professor in the laboratory of cryptography under the Professor Takagi at that time. And then I moved to University of Wollongong since 2018 as a lecturer in the School of Computing and IT. And then I was promoted to senior lecturer from beginning of this year. My current research interest is about post-quantum cryptography, which is one of the topics that I'm going to talk today. So most of you, all of you may know about the NIST post-quantum crypto standardizations. So they called for proposal in February 2016. I was actually the announcement from NIST was from here in Fukuoka at the PQC, I think in Fukuoka 2016, and I'm luckily there. And the deadline was November 30, 2017. In December 2017, then the first round algorithms were announced, and there was 69 eligible submissions. In January 2019, the round 2 algorithm announced, and there were 26 algorithms selected. July 2020, round 3 algorithm announced, and there were 7 finalists and 8 alternatives. And just some months ago, there's announcement of candidates to be standardized. And there is one public encryption of CAMs. This is crystal kyber, and there are 3 digital signatures. One is lithium, the second one is Falcon, and Springs. So as you can see, 3 of them are lattice-based. And they are structures. So NIST also recently put a call for proposal on digital signatures that not based on structural lattice. So I'm not so sure what are the intention, but maybe this is just a threat. No, not a threat, but it just to be safe, because both are structural lattice, and as you know, there's still a lot of research going on investigating the security of structural lattice crypto system, because like we may use a lot of structures to for the attacks. Recently, you may see some trends in cryptography under the name cryptography from group actions. So actually, you can realize those through lattice-based cryptography. You can see most of them appears in isogeny-based cryptography. You can see them also in code-based cryptography. And you can see them also in other topics. For example, the alternating trilinear forms that I'm going to talk today. So today I will talk about one new post-quantum digital signatures that based on isomorphism problem of trilinear forms. And it is in the lines of direction like cryptography from group actions. Is it potential for practical use? So the public key size is around 4,100 bytes. Signature size is about 6,800 bytes, and running time is quite fast. And this talk is based on the following joint work of myself with other researchers from UTS, Germany, and Germany. Yeah. The first one appeared in Eurocrypt this year, and the second one is in April that you may want to have a look in case. So what is the basic idea? The basic idea follows the quite popular idea. Well, we first construct a zero-knowledge interactive protocols for alternating trinary form equivalent problems, and this is inspired from the Goldreich, Micheli, and Wigderson zero-knowledge protocol for the graph isomorphism. So this protocol for graph isomorphism has been used, and the idea has been applied in many areas in cryptography, and then you just apply the Fiat-Shamir transformation to obtain a signatures scheme. So let me recall about the graph isomorphism problem and the protocols from the graph isomorphism problem for you to have an idea, and then you can link to your topic in case. So we have two graphs, G1 and G2. V stands for the set of vertices, and E stands for the set of edges. And they have the same number of vertices. They are called isomorphic if, well, you have a bijective between the vertices that map this vertex to another vertex in such a way that whenever you have an edge between two vertices, then the image of them are also connected. So the graph isomorphism problem asking you, well, I give you two graphs and ask you to determine whether two graphs are isomorphic. And here is GMW protocols. Here you have an interactive protocol between approver and the verifier. Here the approver wants to convince the verifier that he knows an isomorphism that maps the graph G0 to graph 1. So the public key is, well, the public information is G0 and G1, and the private information that only prover know is 5. So this is the isomorphism. So what he does is at the beginning, he chooses permutations of order n. Here's n is the number of vertices, and then he just apply to the graph G1 and send the image to the verifier. For the verifier, just choose a random bit and send it back to the prover as a challenge, and then the prover using the knowledge of the automorphism file to send the response to the verifier. And in this case, the verifier just need to check whether sign of GC equal to H or not. So C here is a challenge. So as you can see, if C equal to 0, then this is phi composed with pi composed with phi. And if C equal to 1, then this is just pi. So pi is exactly H, and then you see that sign of G1 is exactly phi of G1, pi G1 is exactly H there. So the verifications they go through. So this is easy. So this is the basic idea, and then you just use the Fiat-Shamir to transform it into the signature. So in this case of using Fiat-Shamir transformation, then C will be replaced by a hash value of the hash value. So this graph isomorphisms problem were used to design these protocols, and then the security of the protocols is based on the graph isomorphism problem. And in the 80s, the best work case algorithm for the graph isomorphism run in exponential time. And then, but recently you see a breakthrough algorithm of Wabai that can solve in quasi-polynomial time. So basically, this protocol is broken. However, the design pattern, as you can see, it has been utilized in many areas of cryptography. Like the pattern, they replace the graph isomorphism to polynomial isomorphism, and then it may involve several constructions, for example, hidden field equation or the ideal arise from rainbows. And then Kovach, he proposed to use the cluster group actions of elliptic curves to replace the graph isomorphism problem. And then this is just a bond of isogeny-based cryptography that you may have looked at the talk of Hiroshi yesterday. So in our work, we replace the graph isomorphism by alternating trilinear form equivalence. So before introduce about alternating trilinear form equivalence, then let me recall some basic notion of group actions. So let G be a group and X is a set, and G X on X is just a map from G times X to X in such a way that it maps the identity X on X is reserve X for every X in X. And then you have what we call compatibility. So we have whenever we have a G and H, and then you have an action of H on X, and then you X G on X, and it's similar with the action of G times H X on X. The orbit of an element in X is defined by the resulting of the action of G to X for every G in G. And the stabilizer is just the element in G, so that is stabilized X. So it's X on X and equal to X. And the stabilizer is a subgroup of the group. And if the group is finite, then you have this equality. So the cardinality of G is just the product of cardinality of the orbit times the cardinality of stabilizers. The action is cotransitive if there's only one orbit. That means for every element, two elements in X, and you can always find element that map this element to another element. So this action is cotransitive. And in isogeny-based crypto, for example, then you see the transitive action there of the class group. Okay, so let's move to alternating trilinear form. Now here I let FQ to be a finite field of order Q, and a trilinear form is just a map, and this is called alternating if this evaluates to 0 whenever you have a two argument the same. So for example, if you have phi of UUV, so you see that the first two arguments are the same, this will be 0. And then I denoted GL and Q, it's just a set of or the group of n times n invertible matrices over FQ. And then ATF, which is the set of all alternating trilinear form defined over FQ to the power n. So here, GL and Q is a group, and this is a set. And so you have the action of GL and Q act on the set ATF in such a way that for every element in the group, it sends a trilinear form into another trilinear form using this action. So you can easily verify this is the group actions, and then it can define an equivalent relation. So whenever you have two trilinear alternating trilinear form, they are equivalent if and only if phi is obtained from psi by an actions of an element in the group. So we denoted the element actions is on the right. Okay. So what's the equivalent problem here? The decision alternating trilinear form equivalent say that I give you two trilinear alternating trilinear form, decide whether they are equivalent. So in the set that there's one element that maps this form into another form. And then there's another version we call promised ATFE, saying that given two alternating forms in such a way that they are equivalent. So what you need to do is to find element in the group that map this form into another form. And then in cryptography, then we normally use the variant PS ATFE. So this means I have M alternating trilinear forms such that they are all pairwise equivalents. And then the problem is you ask you to find one matrix that maps one element to another element. Okay, so it is not known whether this promise problem reduced to the decisional problem can be expected in exponential time. And then if you look at those versions, you can see that it's easy to give a non-time reduction between the multi-shared problem to the shared problem. So we can assume that the multi is as hard as the shared problem. So let's talk about the hardness of the alternating trilinear forms. So Groucho and Chow, they introduced about the tensor isomorphism complex clause, and later together with Tang, they proved that the alternating trilinear equivalence problem is TI complete. So let us introduce some TI complete problem to support the worst case hardness for the ATFE. The first is come from the tensor isomorphism problems. So a D tensor is just a D-way array. So in this, we just mentioned about 3 tensor only because we have a reduction from any D tensor to 3 tensor 1. So this is the 3 tensor. It's just a cube of numbers. You see that one phase is just a matrix. So two tensor is just a matrix represented by a matrix. But then for the 3 tensor, then you have a cube. Okay, this is 2 times 2 times 2 tensors. And then what's the 3 tensor isomorphism problem? So the problem is, so I have an action. So what's the action? So I have 3 tensors, and then I have a 3 matrix that is X on each side of the cube. And then I obtain another cube. Okay, so the question is, given 2 3 tensors, find the matrix X this tensor to another tensors. Okay, or you decide for the decision problem, then decide whether there exists such a matrix to map this tensor to another tensors. Another isomorphism problem for multivariate crypto is the first one is the qubit form isomorphism problems. So given 2 qubit form, let's see homogeneous degree 3 polynomials, and then decide whether there exists an invertible matrices that map this form to another form, or maybe you get more familiar with the quadratic forms. I mean, in multivariate crypto, then they use more quadratic form than the cubic form. So quadratic form math isomorphism problems say that if you have a 2 triple of quadratic forms, and quadratic form means they homogeneous of degree 2, and decide whether there's exists 2 matrix A and B, so that this map this triple to another triple using these actions. So let me introduce another problem from group theory. This is called the exponential P group isomorphism problems. So given 2 sets of matrices A and B in GL and P, with the promise that A generate a P group G, B generate a P group H, and they are of plus 2 and exponential P. And the problem may ask to determine whether G and H are isomorphic. And this have been studied in computational group theory and theoretical computer science, and has long been known to be hot in group theory, and similar to this problem in multivariate cryptos. And then Groucho, Chow, and Tang, they prove that they are all equivalent under polynomial time reductions. So also equivalent with the alternating form, trilinear form equivalence. So this somehow helps us to support the worst case hardness of the ATFE. So in crypto, then what we use about cryptographic group actions. So let G action X, and this action we call one way if there exists an X in X such that A of X defined by the image of G action on X is just a one-way function. So if you look at CP is be the cyclic group of order P, and G is just the automorphism group of CP. And then you know that G will be isomorphic to GP star. And then you see that GX on the set X, CP remove the identities as the following: G to the power A. So Gx on A equal to G to the power A. And this is one way if and only if this is one way for some G of X. And this means if and if the discrete logarithm problem is one way with a fixed generator. So let's talk about average k-hardness of ATFE. So we call the group is schedule random if it's indistinguishable between the following distribution. The first is you take two random elements in the set X, and the second is just X and Y, where Y is just the image of the action of some element on X. So if we look at the example similar to what we have seen in previous slide, then in this case, we define the action of X diagonally on X times X, send G H into G to the power A, H to the power A. So the random distribution is this one, and the pseudo random distribution is G to the power G, G to the power A, GB, G to the power AB. And this is distinguished between this one, it's just a decision Diffie-Hellman problem. So what we conjecture for the average k-hardness of ATFE is the group action under the ATFE is schedule random. So, well, ATFE, you can represent the instant there in terms of polynomial systems, and in such a case, you can try to look for some algorithms to solve the ATFE. So if you do the brute force algorithm for ATFE, then you can enumerate all the A's, the matrix A, and then you verify whether two forms are equivalent. And this is run as in time exponential time. And then you can adapt a dynamic programming method, and it's run in Q to the power 1/4 n square. And then every case algorithm in time Q to the power n, and it's worked for all but some fraction of the automorphism, the trinity form. There's no known efficient quantum algorithm for the ATFE, and if you look at ATFE, it can be formulated as a hidden subgroup problem over the GL and Q, similar to the case of lattices. Well, as I mentioned, you can represent the alternating linear form instance by a system of polynomial equations, and then you can utilize some attack from multivariate crypto, for example, the Bruckner-based attack or min-run attack. And what we estimated, and this is the complexities of the attacks. Okay, so this is all supporting for the hardness of the ATFE. So now we look at the way how we construct the signatures based on ATFE. So here, the prover wants to convince a verifier that he knows some matrix that map one form to another form. Okay, so here I use a inverse to just for simplicity. So now the similar to the graph isomorphism protocol, then here I have a two alternating trilinear form that are equivalent, and then the secret is just the automorphism that of that equivalence. So the first is the prover choose a random matrix, invertible matrix, and then it just acts on the one form and it sends to verifier. Verifier just choose a arbitrary bit and then send it to the prover as a challenge, and then the challenge just set the response. So if the response, if C equal to 0, then you have B, and then you see that file 0 time composed with B, exactly the file that you already sent. And if C equal to 1, then this is B cancel, you have a AB, and then you have a file 1 composed with AB, A and A inverse cancel, you have a file 0 composed with B, which is file that you already sent as a commitment. So you see that this is actually just follow the same route with the graph isomorphism problem protocol that you have seen at the beginning of the talk. So what is the security of the protocol? Similar is based on the ATFE problems. So you can easily verify the harness verify general properties, saying that if you have a challenge, then you just sample D just for the response, and you set the commitment is just the file C composed with D. Then this is just an acceptance transcript, and this is indistinguishable with the real one. And the soundness is if you have a two transcript with the same commitment, then easily you can obtain easily the isomorphism that maps this form to another form. So it's just similar to the graph isomorphism protocols. Well, this is just with the binary challenge. So in order to be used, obtain the, how you apply the Fiat-Samir to get the signatures, and in order to get enough level of security, then you need to repeat it like a lot of times. So what we want to do, we want to try to extend the challenge space in such a way that we have a shorter public key and repeat less time. So we try to reduce the signature size. And in this way, then we can utilize the idea in isogeneous-based cryptography from the work of DeFeo and Gabret. And then we extend the binary to a bigger space while using more matrices as the secret key, and then for trilinear form. And then the protocol is just the same. Here sign is just the sign of C. So this is defined by equal to 0 if C equal to 0 and 1 if otherwise. So you see that it is similar every time. It stand only sign. So sign here is stand for this one, and then for the response depend on C. If C response depend on C, so for every C in this set, you just choose one of the public key there for verifications. So here is the concrete parameters for 120-bit securities. Then we have four set of parameters, and it gives rise to the signature size. So this one gives us the smallest one with public key size, secret size, and signature size. So it's somehow still bigger than the lithium in terms of O, but not that too much. And then in recent work, we already find a way to reduce that close to the lithium signatures. So of course, I mentioned the signatures that is CQ in random oracle model under the hardness of multi such promisor problem of ATFE. And as you see that most of the work, when you apply Fiat-Samir transformation, the signatures is obtained signatures is CQ in ROM. So we may wonder what's about the security in QROM. So recently, there's a lot of work in QROM security of signature scheme obtained from Fiat-Samir transformation. So in our context, So recently in Crypto 19, the work of Yandri and others, they established a quantum computational unique response property. So what's it, what we need to do in our work, and what does it mean? That means that given two so this is the typo should be alternating trilinear form that are equivalent as to produce two matrices if they exist in such a way that they give you the unique response. So this, if in this case, if you have two equivalent trilinear form in such a way that there exist two matrices that map one into the other one, then this will imply that A and B inverse will be a non-trivial automorphism of phi. So this is, and then we formalize alternating trilinear form automorphism problems, given that given any alternating trilinear form, decide if the automorphism group is trivial or not. If not, then you compute a non-trivial automorphism. And then in our recent work, we confirm through experiment that if you take a random alternating trilinear form and it has a trivial automorphism group with a very good probability, and it somehow support the QROM security of the signature scheme that we just mentioned. We also produce another proof to prove that the signature previously is highly secure in QROM without reducing the efficiency. So the efficiency is still the same. So the idea here is to prove that the protocol is somehow lossy. If you have heard about the lossy identification scheme and the security in QROM of associated via Shamir chain formation. Bad news. So yesterday there's an ePrint ambulance on the attack on against alternating equivalent form, and then as a result, the first parameter set was broken. And other meta sets are not broken yet, but the security level is still reduced. So the thing is here, the first one n equal to 9 is broken, but those are still fine. But of course, the security is reduced. And similar to the case of rainbow, then we need to increase the parameters. In this case, it affects the efficiencies. But in the as I mentioned in the we have checked, but not officially. The updated parameters should not increase too much. And then our recent work here, we in our ongoing work, we found a way to reduce a lot of signature size that we will be released soon in the near future. So anyway, this is the thread, and you may want to have a look at this ePrint for the details. So he used the idea from graph theory, and also involves several improvement of min-rank and Druckner-based attacks. But anyway, as you may, the thing is, this alternating forms group action is quite fast, and it just matrix multiplications. So it's quite fast and easy for implementations. And as you may see, it's, well, in my opinion, it's still potential for post-quantum cryptography construction. At the moment, there is only signatures and ring signature that we propose. And then recent work, there's another proposal for updatable encryptions on ePrint. And they have a strong mathematical support for the hardness. Of course, we need to take care of the Euler's attacks from yesterday. However, they still have a limited construction due to the non-commutativity of the group. And as you may see, for it, also in the case of isogenic cryptography, there are not so many advanced constructions. So there's still a lot of work to be done in this area to understand more about the hardness of ATFE, whether it can be utilized to build more cryptographic protocols or not. And this is all for my talk, so thank you very much for your attention. I'm happy to answer some questions.
Okay, thank you for a very interesting talk, and sorry to hear the bad news.
Well, this happens in our community, yes. So.
And do you have any questions or comments? 販売の方は、ご質問、コメントを使いましたら、挙手をお願いします。
Thank you for the so there is many problems in the case of the tensor isomorphism. So what is the reason for focusing on the alternating linear form problem among the problems in the tensor?
Yeah, so there's as you see, there's an equivalence between the tensor isomorphism and then this alternating form. So there's a bunch of problems that you're right. Why not focus on others? You build cryptographic construction. So what we try to do in this is we found that this one is efficient for instantiation, and then but of course it hints some threat. I mean some weakness for the. So of course in our future work we will investigate some others problems. So yeah, thank you for this question. Yeah, I think yeah, it's true. It's correct. People may wonder why not you others. So because this one, if you can see, this is very easy to look, easy to implement and efficient. So that's what we look at the beginning. Yeah. Thank you.
Do you have any other questions? So I have one question. Could you please show me the parameters setting? So I didn't get the idea of what the difference between the option 1 from option 1 to option 4.
So they are still the same with the same parameters for 120-bit security based on our estimations. Because of depend on the choice of N and Q. You see that here N is small but Q needs to be big. Here N is big but then Q should be smaller. So it's a trade-off. So if you look at the complexity here, you may depend on this complexity for choosing parameters, similar to the case of multivariate crypto.
So the size of the public key is like 6 kilobytes.
So the public key in this case is 4,000 bytes. This is not broken by Bullen's attack yet.
Yeah.
But of course it reduces the security level. So we found a way to reduce the signature size up to 3,000 bytes, but it's not published yet.
Okay. Because I just focused on the net-based signature, so the key size is still larger than the.
Yeah, I think the lithium made around 3,000, 2,000 something.
Yes, for lattice one, it's just 1 kilobytes, 2 kilobytes, like that. So it's larger than lattice based, but it's still smaller than other. Isogenes, right?
Publicly of isogenes. I think isogenes they have a advantage of signature size, right? But we still cannot compete to lattice, of course. Yeah.
Okay, do you have any other questions? Okay. オンラインの方はないですかね。はい、もし質問、コメントがございませんでしたら、終わりたいと思います。Thank you very much for
Thank you very much.